anything. See if I can figure out how to get this screen. I'd like to kind of share full screen, but the problem is once I go to full screen, it hides everything, and then I can't see. Let's see. So if I share now, okay. Now where's my mouse?
Huh. I don't think you're sharing anything quite yet.
Okay, no, I'm not, because I can't. I got my mouse back finally. Okay, so I'm going to share. I'm going to share PowerPoint slideshow there. And with that, I think I don't think anybody's figured out how to share on one screen and actually see like comments and the rest of Teams on another screen, which seems like it would be really useful. But if you go full screen on your slides, it makes everything else disappear. So, but I think that'll be okay.
Don't worry, I'll curate the questions in the comments for you.
Great. Okay, so I'm working on several intersecting projects, most of which intersect in one way or another with Tech and Narrative Lab. And the one I'm talking about today is an effort to take a whole bunch of mobile device data that we bought at a really reduced price from Uber Media, which is no relation to Uber, the car people. So we've got 2.2 billion cell phone pings for Portland, Oregon, and we're trying to use those to build a contact network to understand the spread of COVID-19 in a U.S. city. And generally just learn to work with data that is this big and this kind of primitive. You know, these are really just points with users hooked onto them, but there's a lot of work to be done to turn it into anything useful.
So when you say it's a specific city?
Yeah, we're looking really at Portland, Oregon. And the reason we're looking at Portland is because we have, well, let's see, let me back up a little bit. I want to make sure I don't cover all my slides before I start showing my slides. So yeah, I guess it's fair to say that. So yeah, we've got the data is for a specific city. The thought being that you know the way that a disease spreads, you can model it with differential equations, and that's the way that pretty much all the models work. But it is known that the topology of the network it's spreading over can actually matter. If you've got, you know, really high degree nodes, you know, super spreader events, you know, if there's a big church where everybody goes and sings for a week for an hour every week, you can potentially end up with lots and lots and lots of people infected in that one spot. And that's something the differential equation model just isn't going to be able to pick up. In fact, there are quite a few things that you can't really get a differential equation model to tell you. Differential equation models kind of need a lot of assumptions as input that should be output of a model, but you can't model things that way. If you had a full detailed simulation of who people are, where they go, what they do, who they meet, you could actually push the assumptions down a level and understand things a lot better. So yeah, and so the idea is to have a specific city, not just a city in concept, but a specific city where you can actually know things about it, and you can change stuff, manipulate things, and see what it does. And Portland isn't, in some ways, a particularly great city to do this with, because it's culturally quite homogeneous. It is fairly small. And well, most notably, it hasn't had a huge coronavirus outbreak. They've had some cases, but they haven't been a major center. But the thing that's really good about Portland is we have a synthetic data set for Portland that lets us do some baseline work and make sure we can build a model that runs. And we can then figure out how to make use of the cell phone data kind of relative to the synthetic data. So we have some kind of a reference point. If we didn't have a reference point, there are just too many things we wouldn't know how to do. So we started with a city where we can have something to compare to, and that is Portland. That's the only city that we have this synthetic data for. So yeah, the reason we're doing it is differential equations, like for instance, the excellent work that Raf and Jamie Ringel and people have been doing, model the disease as a set of differential equations. But those equations mostly assume random mixing within the population. And if they don't, you have to actually add more equations. It gets very complicated trying to do anything other than random mixing. They also take the reproductive number. How many new cases does each case produce as an input, right? You have to tell the model how many cases each new case produces, at least in the base case, the R0. And then the model will update that to RT over time. But you basically have to put it in, you have to put in the infectivity of the disease in terms of number of new cases created, which actually assumes a lot. It's not just the infectivity of the disease, but it also tells you a lot about behavior. You know, how many people do people come in contact with? You know, there's a lot wrapped up in that number that you'd like to be able to unpack, but you can't. It also makes it hard to model specific policy interventions. You know, what if I close schools? You know, what's the impact of closing schools on infections in nursing homes? You know, that's indirect. Well, usually you can't pull things apart that much. You know, if I open restaurants at half capacity, what does that do to the infection rate? You know, if I have some idea about people singing in churches, you know, if I have some model of what happens in a church, you know, if we tell people they can go to church but they just can't sing, does that help? Well, you know, you can't put that into a citywide differential equation model, but you potentially could put that into an agent-based model that has, you know, churches in it and people getting infected in churches. If you have an idea about what singing does with aerosols, yeah, you could put that in there and then see what it does to the overall city rate. So that's the kind of granularity we'd like to be able to work toward. And that's kind of why we're trying to do this. So we need a detailed, flexible contact model that's an individual agent-based simulation. And the first step to getting that is you need to know who's coming in contact with whom. And actually, you really kind of want to know why, because you want to be able to manipulate that. You know, okay, we closed schools. Those contacts aren't happening anymore. But, you know, we're reopening restaurants. So those contacts are going to start happening again. So to try to do this, we got 4 months of mobile device location data from Ubermedia. And we got it for $2,500, which is, you know, a tiny fraction of what it would be on the commercial market. They are basically trying to, nobody likes these companies that sell people's location information. And so they would really like people to hate them less, I think. They wouldn't put it this way. And so, you know, to the extent that they can be helpful, they want to be helpful. So we got 2.2 billion pings from mobile devices. About 750,000 different devices, over the course of 105 days between January 1st and April 13th. And this data is interesting because you kind of imagine, a ping every 10 seconds from every device. And that is not what it is. This is data that comes from apps that people are using on their device. When you install a device and it says, this app would like to use your location, and you say okay or not okay. And some of them would like to use your location in the background. Most say, use your location while you're using the app. But there are reasons why you might want an app to use your location in the background. Like, for instance, there are apps that tell you when it's going to rain. Well, they need to know where you are. So if you enable that, it will pop something up when it's about to start raining. Can be handy. On the other hand, the thing you click saying, okay, you can use my location, you're actually agreeing to share your location with the app developer and its partners. And Rand is now one of their partners. So there's a huge market in this, they call it volunteered location information.
Can we pause here for a couple of questions?
Yep.
There's one in the chat, but before we go there, can you talk a little bit about the representativeness of this data set for the background population? Do they give you any information about demographics of the pings?
Yeah, we don't know very much about that. They don't have. I can tell you it's about half of the devices. On the order of between a half and a third of. Well, sorry, it's about between a half and a third of the number of devices is between a half and a third of the number of people in the area. So, for any given group, it's going to be a lot of them. You got to think that children are underrepresented. But as far as, race, ethnicity, income, hard to say. Mobile devices are pretty ubiquitous.
So it's likely that there is high penetration, but probably some systemic biases in the sampling.
Undoubtedly, there are systemic biases, and we don't know what they look like. My guess would be that the people who are more privacy oriented would be less represented. I think that people not showing up in the data has more to do with people not sharing their location than it has to do with people not having a device. You get some people who can't afford a device, not going to have them. And you got some people who just got all the location sharing shut off because they don't want people knowing where they are. Those probably skew slightly different directions, but I don't think. There is literature on who uses their devices variously, and I haven't explored it. The company that gave us the data didn't seem to have good summaries of that.
Okay, a couple of questions before we go on. Details on when you say differential equation models, you mean SIR stuff, compartmental model stuff for the
yes.
Okay, and can you talk a little bit about the synthetic data set for Portland? What does it consist of? Like, what are they trying to do with this?
Yeah. So Raf is the expert on exactly where, how, and why it was developed, but it was developed at, I think, Virginia Tech. It's an interesting thing. It was an effort to get away from PII problems. Thing that this group did was come up with a collection of fake individuals, people who live on the right block or on the right face of the right block and have the right mix of demographic characteristics as far as age, race, income, all that stuff. And all the internal correlations are right. So the older people who you'd expect to be wealthier are wealthier and that kind of thing. The right ethnicities live in the right parts of town, that kind of thing. But yet, when you choose an individual from this population, that actually doesn't correspond to any particular actual individual.
We still there? Oh.
Yeah, we're still here.
All right, I think I just dropped my my AirPods just dropped off. I will go to I'll go to lower tech communication. Can you still hear me?
Yes. Yes. I think we have enough questions for now. We'll save more for later on if you'd like to proceed.
Great. Okay. So they then took this synthetic population and applied a detailed transportation model, figuring out how many trips each of many locations is going to generate, and modeled everyone in the city's movements. And then from that worked out everybody's contacts, who comes in contact with whom. And so I have a data file on 1.6 million individuals that are grouped into, I don't know, a few 100,000 households, and then a list of contacts for each person, or list of contacts between people. And so it's around 1.5 million people, 1.6 million people, and about 19 million contacts on kind of a typical day. There's only one day of kind of typical contacts. And I'm not sure how realistic that is. I mean, it's complete. It's really nicely complete, right? I know for this individual, I know how old that person is. I know exactly who they came in contact with. I know exactly where. That's great, except it's made up. I don't know whether any of it's real. And so with the mobile data, I know a lot less about the people, but the locations are real. So it's an interesting thing to try to compare these two data sets. So there are some real limitations, though, to this data. It is far from complete. So we've got around 1/3 of the people represented. My phone's ringing, sorry. Or about 1/3 as many devices as we have people. And the devices don't report all the time. They estimate about 10% coverage, and we can unpack that a little bit. We looked at a Portland Trail Blazers basketball game, and what you're seeing in the picture is all the pings within a three-hour window around the game in the area of the stadium. You can kind of see the shape of the stadium there. We know that the stadium holds 20,000 people and that it always sells out. Well, we only saw 700 devices. That's 3.5% of the people. And that actually turns out to be, if you take 3.5% of the people and you figure that's what that math is. But anyway, we've got 1/3 of the devices. I won't try to go through the math, but yeah, it all makes sense. So we've got 3.5% coverage. Right, we've got 10% coverage of the 1/3 of devices that we even have any coverage of. So we actually have 3.5% coverage. That's my point. So you think about what this means for contacts, though, it's worse than 3.5, because if you've got a restaurant with 60 people in it, and you've got 3.5% coverage, that means you get 2 people, which actually means you get 1 contact. But if you had 60 people, you'd actually get 1,700 contacts, almost 1,800 contacts. So you're getting 1/1800th of the contacts that you ought to get, which is not good. You can't really do much with that. And that was the first thing we saw. Oh, crap, 2.2 billion pings seemed like a lot, but it's not enough. And so I'm going to actually go through a method we've worked out to try to actually fix that. Because there's a lot of information there. But how can we do some data origami to actually make this useful? And what we've done is we've come up with this idea of a composite movement pattern.
Hmm.
So we can know some things. We have an estimate of where each device lives, its common evening location that Uber Media actually calculates. And we also have an estimate of its common daytime location that they also calculate. We could recalculate that, but they're already doing it, so it's handy. And then we can work out where the device is. Well, we don't want to just use all the pings. Like a lot of people use SatNav when they're driving around. So you leave this string of very, very nice points, 1 second apart, maybe less than a second apart, but you're driving, you're not passing COVID. That's totally not relevant. So most of the pings are not of use to us. We really only we want to know when somebody is stopped somewhere that's not a road. And then we want to work out when people are stopped near each other. So that turns out to be tricky, but we can do it. And so we work out four kinds of stops. One, the common evening location, home and work, like we can get those. Then we have a bunch of businesses that we know about, and we basically can just build a buffer around them and figure out when the device goes to one of those businesses. And count that. And then we can also just look at where devices stop. Where do we get multiple pings from a device in the same place? And we can just average those locations and say, okay, the device stopped here. And so I'm gonna go a little bit more through how we do that, and then talk about how we put this all together into a composite movement pattern. So first of all, home and work. This is relatively straightforward conceptually, although apparently the execution is a little complicated. So they look at the most common place where the device was observed between 7 p.m. and 10 p.m. And not every device has something like that, right? There are people who are out during that time, don't come home in the evening. So not every device has a common evening location, but most do. Also, though, that location may not be in Portland. There are lots of people who show up in the data, but actually live in New York or Seattle. And so we've actually kind of filtered those out. It turned out to be about a third of the pings in the database are from devices that don't seem to live in Portland. But it's over the course of 4 months, right? You keep accumulating these visitors. On any given day, it's not that many, but over the course of 4 months, it ends up a lot of people have been through Portland. So for the time being, we're throwing those out. We may bring them back in later to look at disease coming into and out of the city, but we're trying to just understand the dynamics in the city. Those really aren't very relevant. And then the common daytime location is if there is a place where the device is commonly observed during working hours. Not every device has one of those, but many do. Now, the details of exactly how you think about the same place, that turns out to be fairly complicated, but the intuition is simple enough. Okay, then we need to work out the places other than home and work where the person went and stopped. We've adopted two approaches to this. One is we had a bunch of point locations that we actually also got from Uber Media of businesses that they're interested in tracking people's activity at. They have polygons, detailed polygons of the perimeters of these places that they said they would be happy to share with us for about $3 each, which we don't want to pay and can't pay. So we reconstructed our own. We threw a fairly broad net. We did a 30-meter radius around that centroid, and then as you can see from the picture there, where they come near each other, we do kind of a Voronoi diagram kind of thing where we, it's the centroid you're closest to, and within 30 meters, it defines the polygon. And we had to make that a very simplified polygon so that we could sort through it quickly using PySpark. And if David were here, he would talk about the technology we're using. We're doing this all with cluster, the RAND big data cluster, and a little bit of stuff on AWS using Libby PySpark, which David is a wizard at. Because doing things on 2.2 billion pings, that's hard to do in just Python on your laptop. And a lot of stuff we're doing a lot of it takes maybe half an hour to execute, although there are things we're doing that are definitely an overnight kind of job. So one thing is, anybody who pings in any one of these polygons, we assume they were there for at least 5 minutes, even if they only ping once. And if they ping multiple times, we add those up. We keep track of the time that they spent in the polygon, and record a visit to the polygon if they're there at all, minimum of 5 minutes. And then if they go for an hour without pinging, we assume they left, and then they ping again, we assume they came back. So that's one kind of stop. And then the other kind of stop outside those polygons, if a device pings twice within 10 meters of each other, we then start accumulating pings until we get a ping that's more than 10 meters from there. And then we take all those and average their location and record the beginning and end of that time. So we go from, it might be 1,000 pings, become one location for an hour and a half. And the nice thing about that is that the accuracy, there's about 3 meters on average of noise, but up to maybe 10 meters of noise, maybe a little less than 10. These locations aren't perfectly accurate. They seem to jump around a bit. Well, once you've got 100 pings, if I'm sitting in my desk chair with location services turned on, once you've got 100 pings, you're gonna be within a meter, easily within a meter. You're gonna be within centimeters of where my phone is. You'll probably be able to tell my left pocket from my right pocket, actually, with 100 pings. So yeah, these stops become fairly precise. So if somebody's in a park having a picnic, if somebody else is having a picnic within 10 meters, we'll see them. And if they're more than 10 meters away, then they'll look different. So that's pretty cool. So with these stops, if you go into one of these polygons, we put you in the polygon. And outside the polygons, we do these more organic stops. So then the trick is to put these 3 or 4 kinds of things together into an activity list for an individual, for a device. So at this point, we just assume that you're home for 12 hours, whether we have any evidence for that or not. If you have a common evening location, you spend 8 p.m. to 8 a.m. there. And if you have a common daytime location, we have you at work for 8 hours. Then we basically add up enough days worth of other stops to get a realistic amount of activity for you. Now, how do we estimate a realistic amount of activity? Well, here's where we use the synthetic data as a reference. We know that we have about a little more than 10 times as many contacts as we have people during a typical day in the synthetic data. The synthetic data was designed by people who study people's movement all the time. That's what they do. So we're guessing that's on the order of about right. So we basically composite days until we get about the right ratio till we get to about the right number of contacts. But these contacts are, of course, much more realistic because they're based on actual movement data. That turns out to be, it takes about 3 weeks of activity to get a full day's worth of activity. And yeah, we basically do it, run the contact network, see how many contacts we get, and adjust. And that's how we've been, and keep doing that until we come up with something that's about right.
Can we pause for questions?
Sure.
Cord has a question about how you work with mobile contact versus static contact. It seems from your discussion that you're anchoring very strongly on static contact.
Static contact. Yes, right. We don't have a good solution for actual moving contact. Like if you get into an Uber car with somebody, we're going to miss that. That turns out to be just data-wise, that's a hard problem. I would love, I mean, what I want to see, what I think would fix this whole thing. I mean, if we could do Bluetooth-based contact tracing, where Google and Apple push updates to the operating system so that everybody's phone turns on Bluetooth and reports what phones it's near all the time to some cloud server that Congress says, you go to prison for a long time if you abuse this data. And then if you test positive, you put it in your phone, that goes to the cloud. Everybody you've been in contact with for the last week gets notified. I mean, that would work so well. And it would handle things, Bluetooth would handle things like getting into a cab with somebody. But trying to fish out two devices that move together from this data set is possible, but very difficult, very computationally intensive, and we don't have a solution for it.
And also some clarity on the nature of data. So this is ongoing. The data you're giving you is current as opposed to historical. Like, are they giving you enough information to baseline on a pre-pandemic phase?
Yeah, we have. Actually, I'll show some graphs in a little bit that will let us really see that. But yeah, we have about 3 months, a little over 3 months pre-pandemic. January, February, March, you're starting to see some behavioral change because people kind of know that the disease is out there. But then in April, you get a radical shift. So we're basically treating January and February as pre, and the end of March and through the middle of April as post. And that's not perfect, but it's pretty good. Good enough, given the close enough nature of what we're doing. I'd say it's adequate.
Okay. And final question for this round. Are you doing any analysis of the comparison between the mobility of the visitors you identify in the data set versus the locals? Because it sounds like the visitors seem to have the characteristics of possible super spreaders.
Yeah, that's really interesting. We have not looked at that yet, but we should. The thing that's really interesting about visitors, like the University of Washington models that everybody was looking at early on, predicted that the pandemic would be over by now. And the reason was that they assumed that all the lockdown measures would stay the same the whole time, but also they assumed no interaction between states. So at one point they were predicting Connecticut would be near its peak, while New York was at almost zero. And it's like, well, guys, I don't know if you've ever been to, Southern Connecticut, but it's part of New York. Like New York City's not going to be near zero with Connecticut peaking. Like that's just not going to happen. But they were assuming that state lines didn't ever get crossed. And so as you start trying to mop up an epidemic, people coming in from outside where they aren't in the mop-up phase become hugely relevant. And so I think we're going to need to do more with them. Right now, we're just trying to figure out the dynamics within the city, but I think it's a really interesting question that we need to come up with a better way to explore.
All right, carry on.
Okay, so once we've built the activity list for each device, we then need to come up with a contact list. And we do that in a, I don't know, maybe not the most elegant way, but it computationally is manageable. We basically just quantize all the coordinates to a 10-meter grid and say if two devices are in the same, have the same coordinates once you've quantized them, and their times overlap, then they are in contact. So we can go through basically each grid square. What devices do we see in there? Which ones have times that overlap, and we can make a list of contacts. Device 1, device 2, grid cell, and contact time. And this gets pretty interesting. We can look at, for the 3 kinds of interaction, looking at just one day. This is actually from a little earlier, but it gives a flavor of how this goes. Pre-distancing, we see more people interacting at home than at work. So pre-distancing, we see 112,000 people, 112,000 interactions at home. And this is just, again, one day. This is before we do all the stuff to kind of amp up the density. All this stuff, this is not a composite day. This is just an observed day. So we're getting 112,000, 113,000 contacts at home, and post-distancing we get a few more. And work, actually, we also get an uptick there, not a huge one. And actually, this is because we only have one set of home and work locations right now. And actually, we're going to give Uber Media another $1,000 to give us some updated home and work locations. So we understand how people's daytime location has changed before and after distancing. So that's a flaw right now that hopefully we'll have fixed next week. But the thing that's really interesting is the stop-based things, the neither home nor work, fall to a lot less. In this case, it's a third, and I think as we move forward, we're looking at it's even less than a third, as many contacts out in the world, and that's fairly dramatic. So now I'm going to do some pictures that hopefully will make this all a little less abstract. Okay, here are contacts that happen at home. And unfortunately, this is a kind of a cool, like, zoomable heat map that for some weird formatting problem, I can't get it to work in a browser. It will only work in Teams. The browser built into Teams somehow works for me. Worked fine on David's computer, but on my computer it doesn't work. So I'm going to show static snapshots. So people live kind of all over Portland. This looks pretty much like the density of population. Contacts at home, pre-distance and post-distance. It looks, pretty much the same. No big difference there. Workplace looks pre-distance, post-distance. You can, interestingly, as I flip between here, pre-distance, you can see a lot of activity in the downtown area. Post-distance, see a lot more activity like over here. What that says to me, and this is a residential area. This is a residential area here. What this says to me is that people are working at home. And we actually don't really have the right data to look at that yet. We will next week. But that's about what we'd expect, given that we have these kind of fixed daytime locations. More people are spending time at their home locations. But here's the dramatic one. This is the out in the world, non-home, non-work contacts. Pre-distancing, post-distancing. Right? That is pretty dramatic. That really is. Other than home and work, people aren't doing much. Now, looking at
and
this,
Tim, sorry, that time scale was a 1-day sample for in both cases.
yes,
Okay.
yeah, this is a 1-day slice. This doesn't involve any of our fancy compositing days business, which we've only done fairly recently. So this is a cool graph that Gavin put together from the. This is from the non-amped up, non-composite day data, looking at the contact network among just the sample data as it changes over time. So we see as we move from let's see, we got the holiday week here, first week of the new year. That data looks a little weird because people aren't doing much. People are home. People get back to work January 5th. And we start seeing this. So the blue is the number of contacts between people, activated edges, and the orange is the number of contacts that are part of the giant component. On any given day, the people who are connected to people who are connected to people who, are all connected to each other. If you look at the whole data set, 99.5% of the devices are part of the giant component. There are actually very few that don't ever come in contact with anybody. In the course of a day, it ends up being about a third are part of the giant component. And in our new composite movement profile, almost everybody's part of the giant component again. But what we see here is that between the beginning of January and the middle of May, people are doing a little less. You're hearing more and more news about this virus. I started staying home around here, but the stay home order happened in the middle of March, and you see this radical change. It took a week for people to kind of get the shopping done, and then everybody stays home. Weekends start looking a lot more like weekdays. Previously, you see Sundays, people stay home. You get these interesting exceptions here. This looks like a weird day. Oops. This day here is a holiday. I forget which one. Both of these Mondays are holidays. So yeah, you see this huge shift to distancing behavior. And so we consider, I think we're taking these 3 weeks as the pre-pandemic time and these 3 weeks as the distancing post-pandemic time. Also, if we look at the small components, the tiny components that are not part of the giant component, the blue line here is components of size 2, just where 2 devices come in contact with each other, but they don't come in contact with anyone else. Well, there were quite a few of those pre-pandemic on Sundays, particularly on Sundays and holidays. However, post-pandemic, there are more of them, and they're every day. And the same with groups of 3, 4, 5. And it's hard to read these ones because the scale is wrong. But so you get this behaves like you'd expect it to. And then I'll stop by just summarizing, and then we'll have some more time for discussion. So we now have 3 networks. The mobile device networks are still a bit in draft because we're waiting for new common daytime locations. So we have them both pre and post distancing. So in the synthetic data, in our kind of our reference, we've got 1.6 million people and about 19 million contacts on an average day, giving us a ratio of about 11 contacts per person. In the pre-pandemic graph, we have about 500,000 people producing about 9 million contacts, or about 18 contacts per person. There's some fine tuning to be done on that, which we're not going to do until we get the new work and home locations. We suspect that those contacts are shorter in duration than the synthetic ones. So we have to decide whether we want to try to get that ratio to be about 11, or do we want to get the time spent in contact to be about right, in which case we might want it to stay a little high. But the thing that's dramatic is when we look at 3 weeks post-distancing, even with the flawed common daytime location data, we go from 490,000 people having 9 million contacts to 400,000 having 2 million contacts, 1.9. So our ratio, we got people having about 4 or 5 contacts a day. And that, so if we calibrate basically the pre-distancing against the synthetic, and then apply the same parameters to post-distancing, we get hopefully the actual impact of distancing. So we can then, for instance, tune our model that we're working on in another project to produce historically accurate behavior in the early part of the pandemic, and then switch to the distanced network and see if we get the impact on spreading that we actually see in the data, that kind of thing.
So can you talk a little bit about that integration aspect? Because I think myself and a couple of other people have been having issues with this. So you have an empirical source of information on behavioral change, but the goal is to integrate that empirical information into a model that helps you sort of analyze the dynamics of the pandemic. That integration doesn't seem to be an easy or clear-cut procedure. How have you guys been thinking about that?
Yeah, so we've got I think Jonathan's on this call. Jonathan Lamb is doing a lot of the programming on an agent-based model that we're prototyping in Repast, and we may actually move to C# and do the visualization in Unity because Repast can't handle something that big. But we basically have a bunch of agents that go through their day coming into contact with each other. And when they're sick, there's some chance that there's a transmission when they come into contact with somebody who's susceptible. And we're actually using all the compartments from the compartment model that the Raf Ringel team has worked up. Let's see how to say this clearly. But clearly, I'm not going to say it clearly. So that contact network is right now we're using the synthetic data to say who comes in contact with whom. We're trying to design the model in such a way that we can swap that network out and swap in one of these empirically derived networks. And in fact, switch from one network to another network mid simulation if need be. There are some challenges with that, in that, for instance, the progression of the disease depends on somebody's age. Well, in the synthetic data, we know how old somebody is. In the mobile device data, we don't know how old somebody is. So we're going to have to make some guesses. And I'm not quite sure exactly how we're going to do that or how well we're going to be able to do that. that's a challenge. But well, another thing we might do is use these networks, and actually something I would very much like to do is look at the differences between pre and post, and then use the synthetic data to figure out which edges to shut off. You know, who's not going out, what's not happening, and actually continue to basically add a bunch of switches so that in the synthetic data we can say this kind of person isn't going out, this kind of person is going out, this kind of event is happening, this kind of event's not happening. But it's there's gonna be a fair amount of guesswork, and I'm not sure how we're gonna do it exactly.
Mm. All right. We have like 6 minutes left.
Right.
Any major points you want to touch? And guys, if you have questions for Tim, feel free to. It's open season.
Yeah, open season. I think maybe I'll end the. Let's see. Let me come back to. Okay, I'm going to come back here, and I'm going to turn my camera on. You can actually see me. Yeah, happy to talk. If anybody's got, we can just come off mute and talk. I'll tap dance a little bit on related projects. So one of the main points of this analysis is to be able to feed into the Portland COVID model that I'm working on with Jonathan and Aaron Frank, and some other people. Another objective is working with Carlos, who's also here. We are hoping to use this to look at how people are interacting within the city. Look at the places that different people go, and how do we do community detection? How do we identify different kind of functional groups of people within the city? I did something along those lines on an RIR a few years ago, looking at Los Angeles and using data from Foursquare, which is kind of a weird data source, and was able to identify lots of interesting geographic communities within Los Angeles that made sense. Los Angeles is really big and really diverse, and there are parts of town where, you know, people speak mostly Spanish. There are parts of town where if you're not rich, there's no point in going there because there's nothing for you to do. You know, there are a lot of really different parts of the city populated by quite different populations. And this was a way to get kind of a data-driven view of that. So we're trying to do that for Portland using this mobile device data. Portland, of course, being a much less diverse city, we will see both geographically and ethnically and variously. We'll see how interesting that ends up being. But this data will feed into that also. It also is an interesting resource for just learning to work with big data. And we actually got the licensing worked out so that we get to keep it after the license expires. And if we want to publish from it, we need to clear it with them. We need to clear what we're doing with them, not the publication, but we need to get permission. But they don't think they'll have a problem with that. But we will have these 2.2 billion pings of cell phone data around in the future if people want to do work with them.
Nice. Have you learned any general stylized facts about networks from Portland that you think will extend past Portland to any other city that you might want to model contact in?
I mean, yeah, I think, well, I mean, certainly our hypothesis that every city looks more like every other city than an Erdos-Renyi random network looks like any city. So I think we'll, you know, just knowing things about what a human population looks like as it moves around, I think we'll learn a fair amount. I guess I don't know how to compare. I don't know quite how generalizable Portland is because I haven't been able to look at any other cities yet. And in fact, we're still trying to figure out how to really make this into a network that has a meaningful number of contacts. You know, remember, we are going from 1/1800th as many contacts as we ought to have, hopefully all the way up to about as many contacts as we ought to have. And that's a pretty good trick, right? Our initial contact network was pretty deficient, and it actually doesn't, because of the way combinatorics work. You don't have to amp up the activity list all that much in order to amp up the contacts by quite a bit. So, you know, the procedure I just described does that, but without doing all that, you really can't understand the contact network at all. So we're just starting to be able to really look at the contact network now that we've figured out how to do all this data origami to get it to get enough contact between people.
Any final questions?
Well, yeah, and apologies for being rather in the weeds, but I figure, hey, it's the tech and narrative lab, so may as well have some tech, and the narrative can be about how we're doing the tech. And by the time there are actual results to present, things will be much higher level. But I figured this audience would probably be as interested in how the sausage is made as they are in tasting the sausage. So
I think this was good. This was great.
Great.
Thank you.
All right. Thanks, everybody.
Thank our speaker. And I think next time we have John Welburn talking about systemic risk, high-level concept, high-level framing of what systemic risk means for policy. So we'll look forward to that. I believe that's the 10th of July, something like that. Yeah. Well, have a good weekend, y'all. Happy payday.
Thank you. All right. Bye.